to solve other problems like fluid mechanics, electrochemistry, mechanical stress and strain analysis, and so on. And therefore, the stuff that you can learn by doing heat transfer simulations can also be used for solving a bunch of other problems. Okay, so let me start today, and by the way, this is part A. So the tutorial tomorrow will be a continuation of what I am teaching today, in order for me to finish up talking about multiple aspects of numerical simulations. So the basic idea is that if I have a simple heat transfer problem, suppose some heat enters this body and the temperatures on the other three sides are 0. I can write a governing equation for this problem. I can say d2t by dx2 plus d2t by dy2 equals 0, subject to some boundary conditions, etc. And I can use all that and my knowledge of mathematics to write an equation for the temperature distribution. It will be double summation CNM sine of something, cosine of something, something along those lines. It will be a messy, long, complicated equation. Okay? But the good thing about that equation is that it is an exact solution. In this equation, if I insert any value of x and any value of y, I will get to know the temperature exactly at that point, right? And I will get to know the temperature without any error involved in the calculation, right? Now the problem is that this approach works fairly well for a regular geometry like this. But what if my geometry was like this? Or what if it had a hole inside it? Or, you know, a more realistic geometry like the one you will see in real life will probably not be nice and regular. Most likely it will have some weird, shape, or the thermal conductivity may be a function of temperature, or all kinds of realistic things that throw off this mathematical analysis. This mathematical analysis is truly valid and possible to do only when I have a regular geometry. What do we do if the problem is somewhat more complicated? For that, numerical simulations come to our rescue. So in numerical simulations, roughly speaking, what we do is that we take the geometry of interest and we break it up into a large number of nodes. And we say that, look, instead of finding an equation for the temperature everywhere in the body, all I will do is that I will try to find out the temperature at each of these points Ti, where I would go from 1 to all the way to n, where n is the total number of nodes in my body. So I will not know the temperature truly everywhere. I will only know it at a handful of points on this body. Moreover, this numerical analysis approach will also give us a temperature that is not exact. There will be some error associated with this temperature. Okay? Provided I am willing to live with those two imperfections. The first imperfection is that I don't know the temperature everywhere. I only know the temperature at specific points. And the second imperfection is that even that temperature has some error in it. It's not, I don't know that it is the exact temperature solution. But if I am willing to live with those two imperfections, then numerical techniques allow us to solve these problems in a wide variety of different types of geometries and shapes and sizes and so on and so forth. The good thing is, even though there are these two imperfections that I talked about, I at least have control about the extent of those imperfections. In other words, by increasing the value of n, I can make my solution more and more exact. I can reduce the error to an extent that it may possibly be acceptable to me. As an engineer, if I know that the temperature here is accurate up to 0.01 degrees Celsius, then do I really need a temperature more accurate than that? I probably don't, right? What is the difference between 29.00 and 29.01 degrees Celsius? I cannot even probably measure it that accurately, right? So I'm willing to live with this kind of error. And if I increase the value of n, I can make that error go down even further at the cost of computational time. So the trade-off there is that increasing n will improve my error, but I will have to spend more time or computational resources in doing my calculations. This used to be an important trade-off 30-40 years ago when computational power of computers was fairly limited, but nowadays I have so much power available literally on my fingers, in my cell phone or in my laptop, that I can really ram through these calculations with even a very large value of n. I don't really have to think too hard, for most problems anyway, about computational power. And so that is why numerical techniques have become more and more popular in the past several decades, to the extent that now there are very nice software tools that will do the job for us without us having to see a lot of mathematics, right? So companies like Ansys and others have figured out that it is best to not show people a lot of equations. So they hide all the equations behind the screen. On the screen you only see a nice GUI where you define the geometry of the problem, you show how the problem works, etc. And after you provide all the inputs needed to solve the problem to Ansys, then there will be some calculations that will happen in the background, and it'll spit out a nice temperature distribution that you can look at. That is all very good. It makes it possible for people with even very little training to start using numerical simulation tools, but the danger there is that it is a garbage in, garbage out system. If you provided the wrong inputs, it doesn't have necessarily any intelligence at that level to understand that the results are incorrect. It will give you whatever results it produces without any comments on whether the results are probably acceptable or not. That is a judgment that you have to make, and that is where your judgment, your training as an engineer comes into the picture, right? So somebody once told me that numerical techniques make a good engineer great, but they also make a bad engineer dangerous. Okay, because if you design a bridge using a numerical technique and you're not doing it the right way, then I don't want to drive on that bridge. Simple. Okay, so my goal in today's seminar and the seminar next is to provide you two things. One is a demo of the numerical simulation tool itself to show you how things work, right? But perhaps more important than that, I want to give you a brief overview of the mathematics that happens behind such simulation tools, because almost anybody can do numerical simulations. I think what is more important is for you to understand what is going on in the background, so that perhaps you may design your own numerical simulation tools, right? There are people just like you who graduate with a master's or a PhD and then go work for companies like Ansys and build these tools, right? That capability requires both the core knowledge of heat transfer and fluid mechanics, and also some knowledge of computer programming and coding and all that stuff, right? So I'll start today by giving you a background of the mathematics that goes behind solving such equations, and then I will also begin perhaps today itself a demo of the Ansys numerical simulation tool, right? So the basic idea behind a numerical technique is called discretization. The idea is that I want to take a continuous equation like d2t by dx2 equals 0, and I want to convert it approximately to a simpler form. I want to take this ordinary differential equation and I want to convert it into a linear algebraic equation. Okay, and for that mathematics comes to our rescue. If I have a one-dimensional body, and if I break it up into a number of nodes, node 1, node 2, node 3 and so on, and if I was to focus on the ith node, this is the ith node, this is the I plus 1th node, and this is the I minus 1th node, then you can show using Taylor series expansion that d2t by dx2 is approximately, it's not exactly, it is approximately equal to ti plus 1 plus ti minus 1 minus twice of ti divided by delta x squared, where delta x is this distance between nodes. Okay? This is an approximation, this is not an exact solution. But what that means is that if the second derivative of temperature has to be 0, then I can say that this quantity must be equal to 0. Right? You can think of this equation as a algebraic equation in 3 unknowns. What are the 3 unknowns? Ti, Ti plus 1 and Ti minus 1. From just one equation in 3 unknowns, I can't solve for all 3 unknowns, right? If I have n unknowns, how many equations do I need? I need, in general, n equations. There are some exceptions to that statement, but in general, I need n equations in n unknowns. So, if I am interested in finding out the temperatures at all the nodes, there are n number of nodes. In order to find out the temperatures at all of these nodes, I need to be able to write n equations. If I can write n linear algebraic equations, then I can solve those equations and find out what those n temperatures are, right? In fact, the problem of solving n equations in n unknowns is a very standard problem in applied mathematics, right? We write it in the matrix form. If you remember, ax equals b, and from there, and from there x is equal to a inverse multiplied by b, right? And matrix inversion is a standard problem that I'm sure you all have seen and so on. So this is an easily solvable problem, provided I can generate those equations. And how do I generate those equations? Well, it's a community effort. If all of these n number of nodes can contribute one equation each, then we would have done our job, right? So I will go to every equation and I will demand I will go to every node and I will demand one equation from that node. So forget about the 2 boundary nodes for now. Let us start from this node. I go to that node and say, please give me an equation. And that node says, okay, if in this equation I put I equals 2, then the equation is T3 plus T1 minus 2T2 equals 0. Correct? Everyone following me? If I go to the second, if this is 2, this is 3. If I go to the third, I will similarly have T4 plus T2 minus 2T3 equals 0, and so on. I have only gone to the internal nodes. When I go to the external nodes, these two will contribute an equation based on the boundary conditions. Suppose I provide a very simple boundary condition that the temperature here is 0 and the temperature there is 10 Kelvin, say. Then the simple equations that these two nodes will provide are T1 equals 0 and Tn equals 10. Right? So the equations from the boundary nodes will come from the boundary conditions. The equations from all the other internal nodes will come from this discretized version of the governing equation. I mean, why is this equal to 0? This is equal to 0 because d2t by dx2 was supposed to be 0. That was the governing energy conservation equation, right? So I've taken the differential form of the governing energy equation, I've converted it into an approximate algebraic form, a discrete algebraic form, and that is what is generating the n number of equations for me. Once I generate n equations, I can solve for them. If there are only 5 nodes, I can perhaps solve it by hand, but if there are 1 million nodes, then I will leave it to the computer to do the number crunching for me. Okay, I have demonstrated this for a one-dimensional problem, but similarly I can solve a two-dimensional problem as well. So suppose I have a two-dimensional plate and I have a bunch of nodes inside this plate where this node is the I comma jth node. So my counting has to use two variables now, I and j. So this is t of I comma j, and if there are n nodes in each direction in x and y, then I have n square unknowns. But the principle remains the same. My governing equation is d2t by dx2 plus d2t by dy2 equals 0, which when I discretize will give me ti plus 1 comma j plus ti minus 1 comma j minus twice of ti comma j divided by delta x squared. What is happening here? What is happening here is that I am looking at the neighbor to the right, the neighbor to the left, and where I am. Do you follow? Ti plus 1 comma j is the neighbor to the right, ti minus 1 comma j is the neighbor to the left, and so on. This is d2t by dx2. As far as d2t by dy2 is concerned, that would be ti comma j plus 1, the neighbor above, plus the neighbor below, I comma j minus 1 minus t of I comma j divided by delta y squared. All of this must be equal to 0. I will write this equation for every point inside the body. The equations from the boundary nodes will come from the boundary conditions, and I would have written n square equations in n square unknowns. Okay, and you can see that the scale of this problem grows very rapidly. If n equals 100, then in a 1D problem I have 100 unknowns. In a 2D problem I have 10 to the power 4 unknowns, 10,000, right? And in a 3D problem I have 1 million equations in 1 million unknowns. You might think that's a big problem, but it really is not. It's very easy to solve 1 million equations in 1 million unknowns. These days, with computational optimization and all that stuff, this is not a difficult task at all. This can be done within a few minutes in most cases. Okay? What I have presented very briefly is called the finite difference method. It was the first numerical technique that was proposed and developed. It is also mathematically the simplest to understand. In addition to it, there are two more cousin methods, the finite volume method and the finite difference method. The finite element method. As I said, finite difference is the simplest, but it has its own limitations. For example, here I need my nodes to be defined along the x and y directions, right? What if my geometry has a hole in it? Or what if I have a really weird irregular geometry? Then I will not be able to define my nodes in a regular in a regular orthogonal fashion, right? It is important in that case for us to be able to solve problems where the nodes are located arbitrarily. The nodes could be located wherever you want, and you want to solve the problem there. When that happens, it is usually the finite element method that is most effective. And so most software tools these days, software simulation tools, are either based on the finite volume or the finite element method. And as I said, the good news is that most likely, unless you're working in a very niche area, most likely you don't have to write your own code to do any of this. Simulation tools these days are advanced enough for you to be able to even tell them what equation you want to solve, right? And then whatever physics it is that you want to capture and solve, they are able to solve it for you. Okay? Any questions so far?
So is it all about the rectilinear flow you are mentioning?
Yes.
Is it a rectilinear flow?
It is, yes. So the equations that I wrote in the previous slide were for one-dimensional flow,
It's for
only one dimension. These equations are for two-dimensional flow
that is for dimensional.
in x and y directions. Exactly. I can similarly extend it to 3D, where heat can flow truly in any direction that it wants.
It forms like, because I am very quite new to
Yes.
I am not right.
Yes.
Especially for heat flow.
Correct.
We are working on some material studio kind of.
Yes.
It's quite interesting fields.
Mhm.
That's what I asked.
Sure.
Okay, elementary one.
Absolutely. In the end, after you solve all of this, you will get a two-dimensional temperature map, a contour map, right? In fact, I will show some of that in the research seminar that I will give, where we solve such problems with complicated geometries. Okay? Any other questions or comments? Okay, so what I would like to do is to, let's see, is there anything else that I want to do here? I just want to make a comment here that a number of transport processes are governed by similar equations. For example, heat transfer, mass transfer, electrostatics, to some extent fluid mechanics. In general, fluid mechanics is a lot more complicated, but certain problems in fluid mechanics follow similar equations. I will add a few more which you may not be aware of. Ecology. A lot of problems in ecology are governed by similar equations. So for example, if I have a large space, a large city for example, and if I introduce some invasive species into that state, I introduce, I don't know, dogs or something like that. How will the dog population grow as time passes? Some of those dogs will go here and there, they will reproduce, new dogs will be born, some dogs will die, you know, they will be eaten up by some predators and so on and so forth. Some will leave the state. The dynamics of population growth is governed by very similar laws. Okay? Ecology, drug delivery, even the stock market. There are people who model the dynamics of, I see a lot of smiles, the dynamics of the stock market using diffusion equations. And I can tell you this from my personal experience. When I finished my PhD, I had friends who had done extremely hardcore mathematics related to fluid mechanics, who went and worked as investment bankers for the top banking companies in the world. They did not know anything at all about money. Okay, all they were very good mathematicians, and they were picked up by the best banks in the world because the mathematics is exactly the same. Anybody who can solve fluid mechanics problems can solve almost any other problems in the world. Okay, and so you learn one thing, you become capable of solving a lot of other problems as well, and we will see that that is exactly how these simulation tools are designed as well. Once a company like Ansys figured out how to solve fluid mechanics, they said, okay, let's develop a tool for stress analysis. Then let's develop a tool for heat transfer or chemical combustion or whatever else have you. These equations have a very common thread passing through all of them. You learn one, you've learned them all. Okay. So what I will do in the rest of this, rest of today and the next seminar is that I will give a demo of a typical numerical simulation tool, and we will solve some very simple and then maybe a more complicated problem tomorrow in order to demonstrate how numerical simulation tools work. Okay. My goal is not to teach you everything about numerical simulation tools, but that is certainly a skill that you should learn while you are still a student, for a couple of reasons. One is you have time right now, right? Secondly, it's a very good skill to put on your resume. When you graduate and look for jobs, this is something that companies are very much looking for, because as I said, most companies don't have the time or the capability to do mathematical analysis like we are teaching to you all, right? At the end of the day, it boils down to being able to solve problems using numerical simulations. It's not a big deal to be able to solve problems using numerical simulations. You just need to do it a few times and be able to understand how the thing works and so on and so forth. Okay, and also in academia, as a student, you probably have access to Ansys and other simulation tools free of cost. You'll realize that once you graduate and are out of this cocoon, that Ansys will actually ask you money to be able to use their license software tools, and it is not an insignificant amount of money. It is a good amount of money. Okay, and therefore, since you have access to those tools right now as students, you might as well learn it now rather than later. Okay, so what we will do is that we will switch gears here. Yes. There you go. All right, so let me close this, and this is the front interface of a simulation tool called, a family of simulation tools called Ansys. Ansys is one of the pioneers of numerical simulations, and they are now a fairly large company, and they offer a bunch of different tools depending on which tools you have licenses for. This list can go on quite a lot, but right now I am doing, for the purposes of this demonstration, I am using a tool called CFX, which is a computational tool for heat transfer and fluid mechanics. All right, and the way this flow will work is very streamlined. It says, tell me the geometry. Oops, where is my mouse? There. Tell me the geometry. After that, help me mesh the geometry. When it says mesh, it basically refers to that process of breaking up the body into a number of nodes, right? So Ansys will ask you, how many nodes do you want me to put? Where do you want me to put those nodes, etc. After you've taken all those decisions, then you will go to setup, where you will basically tell Ansys all the information it needs to define the problem. You cannot possibly solve the problem, or Ansys possibly cannot solve the problem, if it does not know what material the body is made up of, right? It cannot solve the problem if you do not tell it what the boundary conditions are. So you have to properly define the problem and communicate that to Ansys in a certain way that it understands. All of that we will do under setup. And then Ansys will say, okay, now tell me, how do you want me to solve this problem? What kind of accuracy are you looking for? How much computational time you have available for me, and so on. There are a few choices of the different types of solvers to use. After you specify all of that, then Ansys will go and actually solve the problem. It will try to hide most of the mathematics behind the scene, but I will show you where to go to look at that mathematics, because you want to verify that things are working as you expect them to work. And then finally, we can look at some pretty pictures, color plots of temperature distribution, contour plots, etc., to be able to visualize what the temperature field looks like. So this is the standard process, the standard flow of the numerical simulation process. We of course always want to start from the geometry. I cannot mesh it or I cannot provide it the material information unless I have the geometry done. So let's start from the geometry. So I will right click here and open up a new window which is already open here. So here is my canvas. This is my open canvas. I can build whatever I want here. I can create any geometry of interest to me and we can go from there. Okay. So here I can say look at, and I can create a sketch for a circle. And this is a two-dimensional sketch. I can specify the diameter of this circle. 20 is good enough. Do I have a keyboard? Will this work? Okay. Until that I can open this and use the keyboard there, right? So I can say 20 meters and then I can go, okay, all right. Then I can go here and say create, extrude, I can select my sketch and I can say please extrude it to 10 meters. And when I say generate, it would have created this cylinder for me. So this is how my cylinder looks like. Okay. This is a very simple geometry, of course, and so I was able to create the geometry in this body. I can do a little bit of geometry development inside this tool, but for more complicated geometries, this also makes it possible for us to import an external file. So if your geometry is available in SolidWorks or CATIA or any other any other CAD tools, you can always import it into this environment. Okay, I can do. Let me do one more thing here just for our demonstration. Let me create one rectangle. And then create one more extrusion using, what happened to my rectangle? Oh, it's become a part of that sketch. I wanted to okay. Oh,
This work here over here by looking at it. Will directly do.
will it help to close this? it's working, so let's go on with it. So actually I made a mistake. I should not have made this square a part of this sketch. So to fix things, I'm going to delete a few things and sort of restart. Let's just start from scratch. So here is my XY plane. I will look at it. I will create a sketch, a circle of whatever the radius may be. (16) is okay. And then I will create a new plane. Sorry, I will extrude this first. Sure, this looks good. So I've created my geometry. Let me create a new plane. This plane is from the face, from this face, look at this plane and create a new geometry of a rectangle. What I'm trying to do is to make a hole in this cylinder. So for that I'll create an extrusion based on this sketch, and instead of adding material I will say cut material, and you can see that I now have a hole in this cylinder, right? So I can do these itty bitty geometries inside, and if the geometry is too complicated for me to do, you can see that even making a simple geometry like this took quite a bit of effort, right? If I have a more complicated geometry containing multiple materials and so on, then it's probably not feasible, practical to do this inside, but I can always import the geometry from some outside simulation tool. So having done this, I think we are ready to leave from here. I'll freeze this and I will exit from here. So now there is a green tick next to the geometry, which means that Ansys says, good, thank you, I know the geometry that you want me to work on. Next, we need to provide information about how to mesh this geometry, how many nodes to provide in the geometry, and where to place the nodes, etc., and so on. And if you're too lazy, you really don't want to do even that much, you can simply update the project, and Ansys, based on some default values, will create the mesh itself. Okay, so let's just wait maybe less than a minute or so for it to create the mesh of interest to us. Okay, when that process is complete, this will get converted to a green tick, and we will know that we are ready to move forward. So one of you were saying that meshing is a problem. And which one is this? Okay, all right. Let's hope it works. It will, I think. It's now starting to do the meshing, and it's done. The meshing is done, and I can now open the setup, and I can edit the setup because I want to provide it information about the material and so on and so forth. So here is my geometry, and this is how the mesh looks like. Yeah, it has about maybe 10 steps in the z direction and maybe about 10 steps in the radial direction. And this really is a very coarse mesh. If I want to have confidence in my results, I really would like to have a much finer mesh. Much finer mesh, in fact. I will not do that for now. to save on computational cost, and let me just do the demonstration using this alone. Okay, so here I am now ready to define what things look like. I'm going to try and do this without the use of a keyboard, okay, because we ran into trouble when we opened this. Okay, so let's see. I'm going to go inside and I'm going to say this is a solid body and the material is, say, copper. ANSYS by itself knows of only a few materials by default, but if you want, you can always insert a new material within. Oh. No, this is going to be a problem. I don't know why this is happening, but all right, sounds good. Thank you. So here is my material. I need to define boundary conditions in this material. So I will say insert a boundary and I can call it the hot boundary, right? This boundary is, say, this. So the curved surface, some heat is entering this body from the outside, and I can say that this is at, I need to now define the boundary condition. Those of you who are familiar with heat transfer know that there are three types of boundary conditions. Either you define the temperature, or you define the heat flux, or you define a convective heat transfer coefficient, right? Here, let me just define the temperature alone. So the temperature here is 10 Kelvin. And when I say 10 Kelvin, I don't literally mean 10 Kelvin. 10 Kelvin will be a very cold temperature, right? Here, temperature really refers to temperature rise above ambient. So I'm saying that the curved surface is 10 Kelvin above the ambient temperature. Okay, please don't understand this literally. It doesn't mean literally 10 Kelvin. It only means 10 Kelvin above ambient. All right. So I will get out of this. I will then also define one more domain, one more boundary called cold, and that could be this perhaps, and the temperature there is going to be 0 Kelvin. So this is at ambient temperature. And any boundary that I do not define will be assumed to be adiabatic. No heat loss through all other boundaries. So basically heat will enter inwards and it will leave from the top, is what we expect to see. Okay? I can go to analysis type and make sure it is a steady state simulation. And under solver control, now this is sort of the nuts and bolts of the simulation. Okay, it is asking you how many iterations to do. It is giving you a choice about the type of residual. It is, a lot of things here that you don't really know what to do about. As an early user, it is okay for you to just leave the default values, but as you become more and more of a sophisticated advanced user, you've got to understand and learn what each of these things mean and do. Roughly speaking, the lower the residual, the higher is the computational cost, but also higher is the accuracy. So I have learned through the years that this number that ANSYS gives you by default is actually too small, or rather too large. I need my residual to be much smaller, and I need the number of iterations to also be at least 200. Okay? With that, we are ready to solve this problem. There's a few other advanced things that I will look at tomorrow when we come back to ANSYS and solve a problem related to lithium-ion batteries. Okay? For now, I think we are ready to proceed. I will close this because I have told it everything I needed to tell it. just one little thing is to give it a suggested initial value, which will be helpful in calculations. And I can close this. And now I'm ready to solve the problem. Oh yes, thank you. So I hit the start run button, and now it's doing all the mathematical mumbo jumbo in the background without really telling me much about it, right? So all those setting up the number of equations that we talked about and solving those equations is now beginning to happen. And it is plotting the residual. Oh, and it happened very quickly. My residual criteria was reached within a few iterations. Actually, it finished 200 iterations very quickly, right? It was so fast because my mesh was actually extremely coarse. If something like this happens, I always go back and make my mesh finer. I don't want, I mean, I can afford to spend more time to solve this problem, right? It happened in less than 1 second. Even if it takes 1 second, 2 seconds, 5 seconds, 10 seconds, even a minute, I can afford to spend that cost in order to get better accuracy, right? And then there are some other things here. For example, you should always look at the residual criteria, the imbalance criteria. You see, it is telling you that the total imbalance in the problem is, pretty much zero, which tells you that you have solved this problem very accurately. Okay, and this happened so quickly because this problem was extremely simple. It was perhaps the simplest problem one could think of, right? Any problem that is more complicated than that will take some more time and effort to solve. Okay, I'm not trying to trivialize numerical simulations here. My students certainly do some numerical simulations in Ansys that routinely take several hours, sometimes more than 24 hours to finish. Okay, all right. So in the last few minutes, I just quickly want to show the results. Where I will create a contour plot of the temperature distribution in the entire body, and that will look like a beautiful temperature color plot of the problem. See, the temperature is the highest around the curved surface, and the temperature is the lowest on the top, and everywhere else the temperature is what it is. Okay, you will see that there is some problem here at the boundary between the two boundary conditions, and that is mainly because our mesh was extremely coarse. Okay, and you can create all kinds of contour plots, two-dimensional plots, line plots, and analyze a bunch of other things using this interface. So tomorrow when we do the next tutorial, I will take up a real life battery problem, and we will solve that battery problem using CFX, and then we will be able to ask a lot of questions to the simulation. What happens if the battery is twice as large? What happens if you flow more air over it? What happens if you do this or do that? What happens if the material of the battery changes, right? We were saying earlier today that if the thermal conductivity can go up, then it will be of a great benefit to the temperature distribution. We can ask those questions to Ansys and say, look, what if I have a material that has twice as much thermal conductivity? How will the temperature change? Okay, we'll do all of that tomorrow, at the end of the day tomorrow during our third tutorial. Okay, so for now we'll finish here in the interest of the other seminar, and we'll go from there. Okay.